In this video, I want to have a look at intercepts and transversals. So last lesson we looked at midpoints and intervals, and in this video we're going to expand that idea so that our intercepts, so these points D and E on this triangle, don't have to be the midpoints of A and B. So the first theorem that we're going to look at says if an interval divides two sides of a triangle in the same ratio, then the interval is parallel to the third side. So what that means in our picture here is that if we have AD over DB, so AD over DB, if that gives us the same ratio as AE over EC, so that means this interval is dividing these two sides in the same ratio, then that means that our lines BC and DE are going to be parallel. So that theorem also works the other way around. So the converse is that a line parallel to one side of a triangle divides the other two sides in the same ratio. So if we knew that DE was parallel to BC, then we would also know that the ratio of AD to DB is equal to AE to EC. So it works both way rounds. So the first example that I want to have a look at says find the value of x and y correct to one decimal place. So we've been given this triangle here, and we know that these two lines here are parallel. What that means is that that line, that interval there, is going to split this side and this side in the same proportion, in the same ratio. So to find x first, we know that x over 5.8, that has to be equal to the other side in the same order. So that would be our 2.7 over 3.4. So that means to find the value of x, we would multiply both sides by 5.8. So we'd have 5.8 times 2.7 over 3.4. Sorry, the reason we should have there, we should always write reasons, is ratio of intercepts. Okay, and if we put that into our calculator, we'll end up with 4.6. So x is 4.6 units. If we then look at y, I want you to start thinking more about similar triangles instead of these ratios that we've been doing. So if we draw these two triangles separately for a second so that it's a little bit easier to see, we've got 3.4, 2.6 and 5.8. And then in this larger triangle, we've got our y here, but we also need to know the length of that whole side there, which would be our 3.4 plus our 2.7. And we could do the same thing on this side as well, but we don't actually need more than one. We only need to be able to match up two pairs of corresponding sides. So if we match those up, our y over its corresponding side, which is that 2.6, would be equal to this side here, so that the whole 3.4 plus 2.7, and you could figure that out first if you wanted to, over the corresponding side, which is that 3.4. And that's because they're corresponding sides in similar triangles. Okay, so then to find y, we're going to multiply both sides by 2.6. And we would end up with 4.7. So y is 4.7 units long. So we can actually extend that idea even further. And instead of looking at triangles now, we can look at sets of parallel lines. So if we have two or more transversals, so in this example, they're these lines coming down here, that cut a series of parallel lines, so we have these three parallel lines here, then the ratio of their intercepts is equal. So in our example, what that means is AB over BC, so this length here over this length, would be equal to this length over this length. So it divides the transversals into equal ratios. Our last example asks us to find the value of x correct to one decimal place. So we've got our three parallel lines running up here, and we've got our two transversals. We know they're going to be in the same ratio. So we're going to start with x on the top of our fraction because it makes it a little bit nicer. So we're going to have x over 3.7 is equal to, and we need to make sure we do the other ones in the same order. So this one would be 5.9 over 2.8. And again, we can say equal ratios on intercepts. And then to find x, we'll multiply everything by 3.7. And we'll end up with 7.8. So that's a few examples of intercepts on transversals.